So, good afternoon, everyone. We will get started now. I think somebody's mic is on. I think Prince Raj, can you just turn off your mic? There is some noise coming through. Okay, thank you. So, yeah, could you just turn off your mic? By the person with the name Prince Raj, please turn off your mic. Yeah, okay. So, again, good afternoon, everyone. So today, day 4, we will do some of the more advanced things in OpenACC and see what there is like before we start on some of the new stuff of the scientific computing using OpenACC. Yeah, let me just check what is happening here. I don't know. Yeah, okay. So previously we had looked at the motivation for using OpenACC, and we also had seen how we could install a supported compiler using the NVIDIA HPC SDK. We were using the PG++ compiler, and we looked at the OpenACC execution model. And also we looked at some of the basic compute constructs like parallel loops, kernels, etc., so on and so forth. We also looked at something called the kernels and async, so which were also useful. Anyway, now before I go on, has everybody tried to install the compiler using NVIDIA HPC SDK? Like, is there any problem? Like, anybody faced any problems? Okay, all right. So I'll proceed. So as we were discussing before, one of the more important things is data management for the whole purpose of GPU computing using OpenACC. Why was that? Because as we discussed 2 days ago, that in the OpenACC and specifically the GPUs, there are separate memories. It follows the heterogeneous memory model, as in the CPU cannot directly access GPU memory and vice versa. So, and if you don't manage your data properly, your program can crash or even produce wrong results, because there will be some garbage values on the arrays, or in whatever location you are trying to access on the GPU. It might either crash or it might produce wrong results. And in case of C or C++, it will silently produce wrong results and you might not even know that it is a wrong result. So you actually have to be careful and you have to be doing the data management properly. The CPU and GPU, as we have discussed before, during the day we discussed hardware, they are generally connected through the PCIe slot. PCIe means Peripheral Component Interconnect Express. It is if you look into your motherboard, it will look as a slot. I'll show the picture. So these slots here, if this is more or less a typical motherboard from, I think, MSI or something, one of these companies, and if you look at this, there are these two slots, this one and this one. These are the PCIe slots. These are connected directly to the CPU, and you can put not only GPUs but even other types of cards in this. So yeah, so all general GPUs are connected to your machine using such a slot. Some configurations, mostly server configurations, can use the SXM. It is the Server PCI Express module. It is the same thing but in another form factor, and it looks like this. So if you look at this picture here, here is the GPU and here is the SXM slot. This SXM slot, one near the bottom of the picture, in that the GPU is not populated. So that is empty. So this is the empty SXM slot, and I think in this one the GPU is already pasted or installed. And this is again connected to the CPUs and so on and so forth. So this is not the PCIe but SXM. It is a variation of the PCIe. So yeah, and this is mostly used in servers and in general home computers or any workstation which has a tower type PC, the tower type form factor. In those mostly you will use the PCIe slot. PCIe comes in various generations, and it is currently I think in 5.0, like that is what is available mostly in the market, but I think 6.0 and 7.0 those are also upcoming. So it started in 2003, 1, 2, 3, many versions have been there, and you can look at it, like there are different speeds, like there can be a 1x slot, a 2x slot, a 4x, 8x and 16x slot. 16x, most GPUs will utilize the 16x slot, and other smaller cards like a sound card maybe, or a capture card or a video capture card and things like that might use the other ones like 8x, 4x, which does not need that much data bandwidth. Those will use the other type of slots, not the whole 16x. But most GPUs generally will use the 16x slot for the highest transfer speeds between the GPU memory and the CPU memory. Okay. So the question is how to handle data. The best part is the compiler can do it automatically. So if you are new to this, you can let the compiler do it automatically, as in the PGC++ compiler or the GCC compiler, whichever you are using. Those are intelligent pieces of program, and they know and they can recognize where the data movement has to be done, and they can actually do it automatically to ensure that your program is correct. But the downside of that is it is not always efficient. Whatever they do, they will think, the compiler will think of some portions where to copy the data, from GPU to CPU and from CPU to GPU, so on and so forth. It might not always be the most efficient way of doing it. And the programmer should ensure it is efficiently done by performing explicit data movement. What is this explicit data movement? That you will actually have in your program, in C program or Fortran, whatever you are writing, in that you have to explicitly mention that please copy this data from here to there and from there to here, so on and so forth. We will see how you can write that, but it has to be explicitly written. And if you are leaving it on the responsibility of the compiler, you don't have to write anything, and you can look at the compiler output to guess where they have actually copied the data. So yeah, and in OpenACC there are two broad types of data directives: structured and unstructured. What are these? The structured ones are like hash pragma ACC data copy out, copy in, and there are a few more. We will look into that. What is a structured data directive? That this thing will generally be followed by a pair of braces, like hash pragma ACC data copy, something will be there, and there will be a brace after, a pair of braces. So within that region, that copy clause, so hash pragma ACC data, and then copy or copy out or copy in, these are the clauses. In that region, that clause will be active. So yeah, that is the structured data directive. So following this directive, there will be a structured block within braces, at least in case of C. And what is unstructured data directive? Like it will be hash pragma ACC enter data, exit data, and after that there will be some clauses like copy in, copy out, things like that. These are not followed by a structured block which is given within a pair of curly braces. So these can be used without having. So for example, if you use copy, there will be a opening brace and a closing brace. but for certain examples or certain algorithms, you cannot use that. So your algorithm is such that you have to independently do a copy of data somewhere, another copy of data somewhere else, so on and so forth. So in those cases, you might want to use this structured data directive. So we will take one example, because making slides for this is not useful that much. So we will actually look at one example on the machine, on my machine. I have written a code, and we will see how it is used. So the mathematical example we will use is called SAXP. What is SAXP? It is a single precision AX plus Y. And this is one of the very important BLAS operations. It is a level 1 BLAS, where there is a mathematical operation between a scalar and a vector. So yeah, so this is one very important BLAS operation. And by BLAS I mean we will look at some BLAS examples tomorrow. But by BLAS is one basic linear algebra subroutines. It was initially written in Fortran. There is the libraries, but this is one of the examples of BLAS. It's called SAXP. And S is for single precision, where this alpha and x, these are taken to be single precision data types like float. And the example we will do is a iterated or repeated operation. So the thing here is, if it is a single BLAS operation, like there is no repetition or iteration, using the GPU in that case, unless n is very large, the size of the vectors is very large, you won't see much benefit from parallelization. But if you are going to be doing a repeated SAXP, like inserted the example I have given over there, x at n plus 1 is alpha xn plus y. So what is happening is, we will start with some x0, and we will go to x1, then we will use x1 to get x2, x2 to get x3. That sort of operation. That will be an iterated version of SAXP, like you have to iterate some n number of times to get some result. What would be the usefulness of such an operation? Maybe in real life or in some other mathematical concept or physics. Like these generally represent what is called iterated maps, and these are very useful in physics and mathematical physics, where these are used to model chaotic systems, so on and so forth. But anyway, we will not look into that, but we will just look into something of this type, which is just the linear algebra operation, like you are doing SAXP. Here x and y are vectors which belong to R to the power n, and by this I mean these are n dimensional vectors. I hope everybody is familiar with this notation. And xi0 and yi. So if you look at the equation given, you have x of n plus 1 is equals to alpha xn plus y. So the vector x changes for every n. So you start with x0 and you calculate x1, so on and so forth. So you need to initially know the value of x0. So in certain physical problems, this will be dictated by the physics of the problem, or what is the initial condition of the system basically. In this case, we will just take random values. I have just taken I modulo 2 and I modulo 3. Y is a constant vector which I have used, and that is constant, as in it does not change with n. So it does not need a separately initial condition. It just has one value where it is I modulo 3. This is the modulo division. I hope everybody knows what modulo division is. And xi0 is the initial condition of x, and that is taken I modulo 2. I is the index, and I runs from 1 to n, and the scalar alpha is taken to be 0.15. So this is a typical example. It's not directly related to some physics problem or some mathematics problem or engineering problem, but you will generally encounter problems of this type where you might have to use this. So this is one variation of the problem. So we will now look into how this looks in code. Okay, I'll share my code. I hope my screen is visible, and I will open the code here. Okay, so yeah, I'll just make it a bit bigger so that it is visible to everybody. Yeah, I hope the code is visible, right? Can somebody confirm?
Yes, it is visible.
Okay, so we are doing this repeated saxp sort of a problem. All right. So yeah, I have declared some integer arrays. I know I have like in the slide I have shown it is belonging to reals, but anyway we can do it using integers. That is not an issue. And I have defined that alpha value as 0.15. Yeah, 0.15 here. And I have defined three arrays which represent those three vectors. I have defined the size of the array to be this one. This is n, the size of the array. And t is the number of iterations we will do for saxp. So over here, what is happening is we are creating and initializing all the arrays. What is this t? T is the temporary array. So when we are doing an update operation like this, we need to have a temporary storage, and then we can just copy that back. So yeah, all right. Now let's. So I have applied some of the data directives. So before what I will do is I will first comment it out so that you can see the effect of it. Okay, I will now open my terminal. I hope the terminal is also visible. Yeah. I'll just cd into my folder. Okay. So first I have now commented out, if you look at the program, I have commented out the data part. And I will also comment out the parallel loops now. Okay. So first of all, let's see what is happening here. So what I have shown in the slide is we will do some iterations, right? So this loop, this for loop controls the number of iterations. So I will go from n equals to 1 to n equals to 50 because I have defined t as 50 here. Then I will do the saxp operation, that this in this temporary array t, I am copying alpha into xi plus yi, because this is just a element wise operation, and it will go over all iterations n, all the elements of the arrays vectors n. And then since I have to do this iteratively, I will copy the temporary vector into the original vector so that I can go and do this operation once again. And now what we have done here is we have, after all this operation is finished for p number of iterations, we have taken sum of the elements. This is just done to check the final value of to have a check, right, so that we can see if the number of steps done is being done correctly or the operations are being done correctly. So first of all, we will compile this. And to compile this, we should remember, before compiling this, we should remember that this is now currently serial. No data clause is given, no parallel loop clause is given. So I will now compile it. It is now compiled. By the way, let me show you that in this machine I have one GPU, which is the Quadro P620. So one GPU is there. Now I have compiled it, so I will now run it. Yeah. So it will take some 5 to 6 seconds. I have executed it. Let me see. It is doing some summation. Output is given. Now if I just do time to find out how much time it is taking. Yeah. So it is taking around 5 seconds to execute it. Okay. All right. Now, so this is actually a very parallel operation, and you might be interested to do this operation on the GPU. So how you can do that? You can just copy, you can just put the hash pragma ACC parallel loop here. Okay. Like we have discussed in the previous class, if a for loop is there, you can parallelize using this. So let's compile it once again. So I have given this flag minfo equals to Excel. What does this flag do? It will show you where GPU code is being generated, what data copy is being done, so on and so forth. So now if you look at the compiler information, you will see it is saying in around line 30 it is generating GPU code. So over here it is generating GPU code, and again in line 30 it is generating something called the implicit copy in of y, x and t if not already present. So this gives you the hint that even we have not given any data clause, correct? I have commented out this data clause, but as I said, compiler knows what it has to do so that this execution is correct. So what it is doing, wherever it is encountering a GPU execution, like it is encountering a hash pragma ACC parallel loop here, it is generating that copy. Okay, so yeah, again it is doing in the next step also. But if you see, this is inside the for loop. So this is important. So we will first execute it. Let's see how long it takes. So this is interesting. What is interesting here is it is actually taking more time than what it took to do it on CPU. Can anybody guess why?
Because you haven't specified exactly what data is supposed to be in GPU and CPU. So the compiler is doing it automatically.
Yeah,
And as
but
you
then
said, it's inefficient.
correct, because it is trying to copy at every iteration step, therefore it is inefficient. But if you think about the problem, like what are we trying to do here? We are having one vector x, we are multiplying each element by another number alpha and adding another number, another vector y to it. And we are repeating this process. So it is actually not necessary to copy the data from CPU to GPU, do the operation, again copy back to the CPU. That is what is actually happening here. If you look at the compiler output, it is generating a copy in which says copy in data from CPU to GPU, and after that it is also copying the same thing out, if you see here. So that way it is actually not efficient. It is doing it for every loop iteration. But we do not need it to happen like that, because between different iterations the data can stay on the GPU, right? Because there is no other operation being performed on the data. Therefore, that data can actually stay on the GPU. So how do we ensure that? This is what compiler is doing for us, but this is okay. It will give us the correct result, but it is not efficient. So to do it efficiently, we will do this thing. So what we are saying here is hash pragma ACC. This is the standard. Now it says data. Now we are saying one copy in, one create, and one copy. Now I will explain what these three mean. Okay, what is happening? The final. Let us first think what is our target. We want to find out the sum of the elements after n iterations or t iterations. Correct. We have t iterations, and we want to find out the sum of the elements of the vector x. So we need to, if you think about it, copy in the value of x, do all the calculations, and then copy it out after all the iterations are finished. So that is what is done here. Copy x 0:n. What it does is copy, when it is encountered in a program, it will copy in the values of x from 0 starting at index 0. What this 0:n means is it will start at index 0 and copy n length. That is what we have, a vector of length n. So it will copy this, and when it exits from here, it will copy it out. And we need that because we want to take the summation. Okay. There is this another vector y which is just used for the addition, because we have alpha x plus y. that is used in addition. So that value we need to copy in because we need to do the mathematical operation. But that value is not needed afterwards. So there is no point copying it out. So what we have written is only copy in. Copy in will just copy the value in and not copy it out when the structured block ends. Same thing goes for alpha. Alpha is another value which we have initialized here, and we do not need it here separately. So we just copy it in. There is no point copying it out. And there is this t. T, there is even no need to copy because there is no value. Anyway, I have initialized the t to 0 here, but t, there is no initial value is required because t will get initialized here itself. So we do not need to copy the value of t. We just need to create the memory space for t on the GPU memory. So we have given the command create. And again, this 0 to n, 0 to n, this means that start at index 0 and have a length of n. Is this part clear to everybody? This is very important. This is where either you will learn GPU or you won't. This is the whole part of it. You have to be able to handle GPU data. So I hope this is clear to everybody. Now let's run it.
Um,
Yeah.
wouldn't you also have to copy the value of copy in x 0 to n? Because to do the operation, you need x and y and alpha.
Yeah, I have copy. I have put copy x 0 to n.
But okay, so what's the difference between copy in and copy
Yeah,
x?
yeah.
Copy is supposed to be output, right?
No, copy is, it is like copy in plus copy out. So once you encounter a copy, when the program sees there is a copy, what it will do is it will copy in x, and after this region is finished, it will copy it out.
Okay, so okay, the
Yeah.
both of them are encapsulated in copy. Okay.
Yeah. And if you just want to do one direction, either you want to do copy in, you have to do copy in, or if you have to do copy out, you can do copy out. All right. Now let's compile it and see what is the difference. Now, yeah, if you now see, this was compiled without using the data directive like what we had done, and this is compiled using the data directive. What you see here is it is generating the copy in whatever is needed in line 28 is here. So it is not generating it inside the loop. Only inside this n loop, it is just launching, sorry, yeah, inside the n loop, it is just launching the GPU code and GPU code, and it is creating the loops. So what is happening is, uh, data copy is being done only once, and inside the loop that is not happening. So we expect it to be faster. So we'll just run it. Yeah. So you see the result is correct. 9,000, 9,000, 9,000, the result is correct. But the time required is way lesser. So in case of CPU, it was 5 seconds. When we had put data, without putting data, but just allowing the compiler to do the data transfer, it took 12 seconds. But if we now have, since we have put our own data directive and made it efficient, it is just taking 2 seconds. So it is quite optimized, and it is executing almost twice as fast. Like compared to CPU, it is executing twice as fast. So as you see, the data copy operation is actually very important, and if you don't do it properly, you will be in trouble, and it will actually become slower than what you can get using even CPU. Okay, let us just play around with some of the things here. As Swarnim was probably asking, what is this copy doing? So let's just do copy out here. Let's check what happens. So if I give copy out here, the value of x is not copied. So if you run it, okay, I think it will generate a copy out, a copy in. All right, so let's see what happened here. It is again giving 90,000. which is the answer, but okay, let me just see. Let me just print the value of x here without doing the sum. But then if I print the value of x, it will be quite a large number. Yeah, I'll have to check what is happening with copy out. I am not understanding it at the moment, but if you actually see it in just with copy in, like I think he was asking, like if you just don't do copy out and you just do copy in here, what will happen is the sum will change because it is actually not copying the value outside to this loop. I will check why it is giving the same answer with copy out, because anyway x is becoming the same, it is not updating here. I will check that, but if you see that if you are using only copy in, the answer is actually different. So you are just going to work with whatever data you have created here, and that will happen. Let's see what else can we do in this one. What else? Okay, so this is more or less how you can control the data. This is where you are using copying the data here, and this is the structured one. As I said, there was something called the unstructured one, where you can use, you don't have to use a structured block like this. So I will use the same example to show that one. Okay, so this is using unstructured data. If you see now, again the program is the same, and I have actually done a copy in x0, y0, alpha, hash pragma acc enter data. We are doing copy in, and we are doing the same thing, create. Now here there is slight difference. This will be encountered, this is called, the clause is enter data copy in, and there is the exit data copy out. I will come to the loop here a bit later. Okay. So what we see here is you cannot use with enter data and exit data, you cannot use copy. First of all, you have to remember that you cannot use copy. Either when you are entering, you copy in, or copy, or while you are exiting, you have to copy out. So let's see first how this looks. Yeah. So if you see here, after 25, it is generating the copy in x, y, and it is also creating that variable t. After all that loop is done, it is again generating all the copy out. Okay. Now let's execute this and see. Yeah, you see the performance is almost the same. 2.15 and the sum is also matching and things like that. And now let's see if it actually works with copy. Yeah, so in entered data, you cannot use the clause copy. You have to either copy in or copy out. So it has to be copy in. So what is happening? You will copy in the data here, you will do all your operations, and you will copy out the data there. Again, let's look at the So if you see, it is saying that it is generating around this loop, it is generating an implicit copy in of yx if not already present. What does this mean? Well, while launching this loop in GPU, the program does not know that we have done this. To let the program know that we have done this, we have to give another clause called present. What does present mean? I am telling the loop that whatever data you need, x, y, and t, is already present on the GPU since we have done this. So let us now compile it. Yeah. Now you see it is not generating the implicit copy-ins if not already present. So we will do it here as well. We will tell the GPU that you do not need to do it, it is already there. Now let us look at the, yeah. See, now it is saying that generating present, that the GPU knows the data is actually present, whatever is needed. Now we can run it again. Yeah, again sum and performance is almost the same. So this is more or less what the structured and unstructured data clauses are. In certain cases, if you know that your thing will be contained within a structured block, you can use a structured data copy like we have used in the previous one. Or if you want to see if your algorithm needs that you need to have separate copy in, copy out separately everywhere, you can use these unstructured data directives. Okay. Now we will come back to one more important thing. Okay, I'll stop presenting here for a second. We will now look at what are called reductions. I think this is one of the most important parts. Like if you have to do, say let's say like in the example we had done, something like the sum of the elements of an array or a vector. So you need to be able to do sum equals to sum plus a of I. If your a is the vector, you need to be able to do that. But then with expressions like this, there is a problem. The problem is if we are using a parallel loop in the for doing the update, sum is a single variable which is accumulating all the addition values, like it is getting accumulated in sum. So what might happen is, it might be that since there are parallel threads, there are some thousands of threads executing it, it might happen that they might try to update the value of sum simultaneously, which is not allowed, and it might cause errors. So what has to be done is, it has to be done such that there is no simultaneous update of the final accumulator sum. So there are certain ways of doing it. One of the ways is using something called a reduction. The usage looks like this. What is the usage? The loop you write is the same, hash pragma acc parallel loop reduction plus colon sum, and then you write your loop. What this reduction says is, using the operator plus, you will perform an accumulation or a reduction on the variable sum. It will be done internally so that you don't have to worry about doing it, but you have to write this reduction so the compiler knows that there is a accumulation variable sum in which the operation plus is being used. What it does internally is, it will create for every group of threads one local value of sum, and when the data region ends, when the loop region ends, it will perform one complete summation to have the final sum ready. So you can do not only addition but various other value operations, like you can do addition, multiplication, min, max, all these unary and binary operators as well. And yeah, so there is something called the initialization value. For example, for addition, it is given as 0. So if you like do not, like as I said, each and every thread, group of threads will for every thread there will be one local value of sum that it will be initialized with 0. that is very natural for addition, and for multiplication that will be initialized with 1, so that the local sums which are being done are not erroneous. If you do not initialize it, there could be erroneous values inside that local sum per thread what you have. So to avoid that error, they are being automatically initialized with either 0 or 1. Okay. So let's look at an example. I will go back to the same code. Yeah. So where can this be useful? Well, this can be used over here. Again, we have a sum which we are doing here on the CPU, because we are doing a copy out and then we are doing the sum. This operation can be done on the GPU, because again it is a parallel operation which can be done on the GPU. So what we will do is we will remove this copy out and we will have a parallel loop here. Now we have to give, first we will not give the reduction. So we are now saying that we will perform the sum using ACC parallel loop. Yeah, now, okay, I'll make this bigger. Yeah. If you now look at the compiler output, we have not given a reduction, but the compiler identifies that there is a reduction is needed. As I said, compilers are intelligent. Compiler identifies that there is a reduction needed and it will implicitly generate it. Or we can mention it like this. Sum. Yeah. Over there the output was, it was generating it implicitly. Over here if you see, it is just saying generating, because it has seen that I have given the reduction here and it is therefore generating it. So let's run it. Yeah. So again you see it is same. See, this is not a very intensive operation, so you will not see that much of a time difference in the timing of it. It will be very less, but yeah, this summation is now happening on the GPU. Okay. So this is how reduction works, that whatever operation you need to do, which is type of an accumulation, either you are doing a multiplication or a some addition or something else, all these accumulative type operations, they need to be performed with this reduction. So this is one of the important things, because there are a lot of applications, and we will see it tomorrow. Like most of the BLAS operations, like matrix multiplication and BLAS level 2 operations, where you use a dot product and things like that, those need this type of reduction. Yeah. Somebody is saying something? Yeah.
Like at first it appears that the summation operation is like dependent upon the previous summation. I believe it is still using some like I wanted to understand like how is GPU actually parallelizing this kind of operation? Is it like kind of divide and conquering operation where it's like summing first certain rows and then
Yeah,
third?
I'll come. So what it will generally do internally is, what it will do is, for this reduction, let's say there are how many data elements are here? Some 9 lakhs data elements are there. We will not have that many threads, correct? So using, let's say we have 128, we are over here probably using a vector length of 128. Okay. So what is happening there is, let's say one thread is doing 5 summations one by one, and there are many such threads. So together there are that 9 lakh by 5 number of operations that has to be done. So for each thread, it will have its own sum value internally for every thread, and in that thread they will do it serially. So let's say there is thread 1, let's think of it in that way. There is thread 1 which has its own sum. Let's say that it is doing the summation for index 0 to 5. It will do that part and store it in its own sum. Thread 2 now will do parallelly with thread 1 from 5 to 10. index 5 to 10, okay, and it will store it in its own value of sum. After all the threads finish their individual sums, it will again collapse that sum into one sum. Do you understand like the sort of logic what is working?
Yeah. It's basically divide and conquer type
Yeah,
operation, right?
yeah. All right. So reduction again is a very useful thing and it is needed for many of the different operations we do. Especially in the scientific computing part where you have to do vector addition, vector multiplication, matrix multiplication and things like that, this becomes very useful. Okay, and so this is more or less what is important for reduction. And I think if you look at the OpenACC this thing specification, you will, as I have shown you, it can be used with multiple other types of operators, multiplication, so on and so forth. Okay, I'll go back to my slides. Yeah, as I said, you can use it with min, max, and things like that. And one of the last topics for the day is multi-GPU programming. This is a bit advanced, but it is quite interesting to see. Let's say you have multiple such GPUs like what we have available in your machine. You have 2-3 GPUs available in your machine. How can you use them to do more work? So it can be done using either OpenMP or MPI. We will use OpenMP because we had initially in our beginning classes, we had seen how you can use OpenMP. The main function which is needed is called ACC set device num. This function is present in openacc.h header file. What the function call does is, it will take a device ID as shown and it will take ACC device NVIDIA. I have written NVIDIA, but it can take Radeon also if you are using the AMD GPUs. So device ID and ACC device NVIDIA. So let's say if you have 4 GPUs in your system, the device IDs will be 0, 1, 2 and 3. If you have 2 GPUs, it will be using 0 and 1. And what we do is, we use different OpenMP threads to control different GPUs. So if you remember, OpenMP threads used to operate in parallel, correct? Like you have 2 threads which used to execute parallelly. Now what we are doing is, using this function ACC set device num, we are attaching one of the GPUs to one of OpenMP threads. So as the OpenMP thread executes in parallel with another OpenMP thread, therefore multiple GPUs can be executed in parallel using different OpenMP threads. So again, we will come to a code example. Okay, so as I had previously shown, this machine which I have, this only has a single GPU. So I will use another machine. So I'll just log into that machine first. Yeah. So now if I run the NVIDIA SMI command here, you can see this machine has 2 GPUs, 2 RTX 3090 GPUs, and the GPU number, this one is 0 and this one is 1. So this machine has 2 GPUs and therefore we can do multi-GPU programming on this machine. Alright, now let's look into the program. Again, it is the same program, but what are we trying to do here? We will do the same SAXP operation on both the GPUs. Okay, I'll have to show you how that looks like. I am monitoring the GPU in this one. So I will just go into my folder here, desktop, OpenACC. There. Okay, before I compile, let's look at the program. I have again created the same x, y, and t, and I have initialized the same x, y, and t. I have actually changed the values here. So the sum variable will be a bit different, but okay. Now, what are we doing here? I am now launching a loop. Again, if you now see here, we are using the unstructured data directives. What are we doing? We are creating a normal loop which says, first one, it goes from d equals to 0 to 2, less than 2. So it goes from 0 and 1. ACC set device num d and ACC set device NVIDIA. So this d variable goes 0 and 1. And what it does is, after that, it encounters this one. So essentially what happens, first for GPU 0, the data is copied in. Then for GPU 1, because next d++ it will make d equals to 1, for GPU 1, the data is again copied in. Now what we do, we launch another loop, d equals to 0, d less than 2, d++, but we launch this with OMP parallel for, so that d equals to 0 and d equals to 1 will execute parallelly. Now we again say ACC set device num d ACC device NVIDIA. So we are again now controlling the device d, which will be 0 and 1, and we are doing the same thing. We are writing present, and we are doing the sum. And over here we have written print sum from GPU percentage d is percentage LF sum. So let's now run this. Now you see both the GPUs are being utilized 99-98%, and the sum from both the GPUs are the same, and it is coming sum from GPU 0, sum from GPU 1. So if you have noticed here, both the GPUs started executing the code. Like if you had noticed in this portion, I will run it once again. Keep an eye out here where I have marked the 0%. See, both become 99%, 98%. So it is being utilized fully, and it is now finished. Let's time it. It is taking around 6 seconds. Why? Because again, there is a lot of copy operations involved. So it actually does not make sense to do an operation like this on the GPU. This is again on 2 GPUs. This is fine for doing it on a single GPU. It will actually take more time here. But anyway, you have to understand that we are doing 2 SAXP operations. So it is actually taking quite a bit of time, but then since it is executing on 2 GPUs and the system size is not big enough, this is not that impressive, but in actual big problems, this is useful and very important. Yeah, but then what is important is you have seen how both the GPUs can be used. I hope this part is clear. How we are setting a GPU number, copying the data. We are again setting the GPU number, set device num, you will set the GPU number with D inside the OMP parallel loop and then execute it. We can put, I think, OMP parallel for here as well. Pragma OMP parallel for, so that that is done in parallel. Let's check that one once. Yeah. So now, okay, what happened here? There was a seg fault. Okay, I have to check why if I put a parallel for here, it is seg faulting, and I'll have to see that. I think it is because of that unlimited. Just check it once again. Okay, there is some issue, like I am not able to put a parallel for here. Ideally, it should work, but I will check it and get back to you. But Yeah, this is the important part where we are executing the same code on two GPUs, and that is giving you directly the results. Yeah. So from both GPUs, we are getting the same result and within a fixed amount of time. Okay, so I hope this part where we are executing the code on two GPUs is clear. I hope that is okay. And again, we have used the reduction here, we have used present here, so on and so forth. We don't need to copy out because we are not actually copying out of this loop, out of the GPU, because this sum can also be performed there. And yeah. Okay, like this is also important. If you see the output here, it is actually saying that it is generating an implicit copy of sum, because technically this should be done. But yeah, this is fine. If you want to put copy sum here, it is fine. If you don't want to put implicit, is fine. So this one, there is no such issue. But in other cases, you should put the copy and copy in, copy out separately. Okay, so this is more or less what is about multi-GPU programming. So if you have two GPUs, you can use OpenMP to address the two GPUs separately and execute code on it. Okay. So it is almost 3 o'clock now. So before I close, maybe our lectures and classes are till on 25th, next week Saturday. We have not kept anything on Sunday 26th, but if you guys are interested, you can mail me, or we can have a discussion on 26th. Like if you have some application which which you have already in C or C++, and you want to execute it on GPU, and if you want to discuss how you can parallelize some application, you can mail me, we can have a discussion regarding that. Okay. So, all right. And therefore today's work is more or less done. What we will do next day is we will start our the final part of our thing, where we will apply whatever we have learned to different scientific computing applications, which is the important part. We will do multidimensional numerical integration. Like you have to do a double integral or a triple integral on a computer, how you can accelerate this. The important part, why integration is an important example, because as you increase the number of integrals, you have a single integral, that is fine. But once you get a double integral or you have a triple integral, if you are going to do using some method like the trapezoidal rule or any other rules like that, the number of evaluations you have to do increases with dimension. That is called the curse of dimensionality. Like if you have a domain for a single integral from 0 to 1, and if you divide it into 10 smaller pieces, you have 10 summations you have to do for doing an integration. But if you have a 2D domain between x goes from 0 to 1 and y goes from 0 to 1, and if you take 10 divisions across both directions, you need to do 100 evaluations. Similarly, if you go to 3, 4 and 5, the number of evaluations you have to do increases. So multidimensional numerical integration, it is one of the examples where you can use parallel computing, and you can do it on GPU. And for examples, we'll also look at some BLAS operations like matrix vector operation and matrix multiplication operations. And finally, next day, tomorrow, we will look at how you can solve linear equations. So these three are our target for doing tomorrow. I will write the code and show it to you, and we will see how we can do it quickly using GPU. Okay. It is 3 o'clock. Anyone has any questions regarding whatever we have done today?
I had a question.
Yeah.
Can you give some reference for the content that you discussed today, in terms of book or some other resource?
Yeah. So maybe I will show you. Okay. So if you go to the OpenACC's website, you will see there is get the specs. OpenACC specification 3.2. If you look into this document has everything. Like whatever you need to know about OpenACC, from the memory model to execution model to everything, whatever is needed, you can find in this document. This is published by OpenACC, and this is very useful. Apart from this, there are a few books you can Google up. OpenACC books are there. For example, this book is actually good. OpenACC program for programmers, concepts and strategies. And there are many books. So yeah, these are the material where you can refer to. But more than this document is more than enough, I believe, for learning how you can program with OpenACC and all. Like we are not going to discuss every API item which is there, but you might need to use some of these for your particular region, and you can find them over here. For example, today we discussed this get num devices, set device type, things like that. And there are many more functions which can be used. So those are all available in this document. Okay. And anything else, anybody? If not, I will stop the presentation here, and I'll also stop the recording, and we will meet tomorrow.